Here is what was supposed to happen. A $10 billion telescope launches on Christmas Day 2021, unfolds a sunshield the size of a tennis court at the second Lagrange point, a million miles from Earth, cools its instruments to 40 kelvins, and begins collecting infrared photons from the earliest structures in the observable universe. The engineering works. The optics exceed specifications. The data arrives. The models are confirmed. The textbooks add a chapter. That was the plan. The data arrived. The models were not confirmed. And the chapter the textbooks need to add is not the one anyone expected. Radiation is the boundary of the body, as the last video explored. The constraint that shielding cannot fully solve. JWST encountered a different kind of boundary, the boundary of the instrument. And when the instrument exceeded its own design expectations, it did not fill in the gaps in existing models. It exposed new ones. 3 years of observations from JWST have forced revisions to at least 3 theoretical frameworks that had been operating largely unchallenged. Galaxy formation in the early universe, atmospheric chemistry of sub-Neptune exoplanets, and the mechanics of star formation in protoplanetary disks. None of these revisions have overturned fundamental physics. All of them have made the questions harder. And the distinction between those two outcomes is exactly the kind of thing that headlines tend to lose. Start with the galaxies. Within weeks of releasing its first science images in July 2022, JWST began identifying objects at redshifts above 10, corresponding to a universe younger than 500 million years. The Cosmic Evolution Early Release Science Survey, led by Stephen Finkelstein at the University of Texas at Austin, was among the first programs to report what appeared to be a problem. The galaxies were there, at the expected distances, but they were too bright and too massive for their age. The standard model of galaxy formation, built on decades of simulations, predicted that structures at those redshifts should be small, faint, and rare. JWST found them in numbers that exceeded predictions by roughly 2 orders of magnitude. The headlines wrote themselves. Cosmology is broken. The Big Bang model is wrong. The standard model cannot account for what we see. If you read any science news in the summer of 2022, this was the story. Hale was not planning a video about galaxy formation. But the CEERS data kept appearing in unrelated papers. Galaxies at redshift 13 or higher, in studies that had nothing to do with early universe cosmology. When a single dataset starts showing up in other people's work uninvited, something structural is happening. Here is what actually happened, and it took roughly 2 years to sort out. The initial mass estimates for many of those early galaxies were too high. The instruments were still being calibrated during the first observations, and the flux measurements that went into the photometric redshift and mass estimates carried systematic uncertainties that inflated the numbers. That accounted for part of the excess. A second correction came from a class of objects that nobody had seen before. They are called little red dots, compact, red, faint in most wavelengths, but bright in infrared. When astronomers first flagged them in the CEERS and JWST surveys, they assumed these were ordinary galaxies, just very massive ones seen very early. Spectroscopic follow-up revealed something stranger. Many of them contained supermassive black holes actively consuming gas, and the light from those black holes was being counted as stellar light. That single misattribution inflated the mass estimates dramatically, making the host galaxies appear far more massive than they actually were. In some cases, the black hole was as massive as the entire stellar population of its galaxy, a ratio wildly different from the roughly 0.1% observed in the local universe today. These objects have no known counterpart at later cosmic times. They appear early, they shine briefly in cosmic terms, and they vanish from the census by the time the universe is a few billion years old. The discovery of little red dots solved part of the abundance problem, but it created a new one. Why do these early galaxies host black holes that are so disproportionately large relative to their stars? And what happens to those black holes afterward? Those questions did not exist before JWST. Now they sit near the top of the priority list. After the calibration corrections, after accounting for black hole contamination, and after revisiting the photometric models, the number of genuinely, quote, zero galaxies shrank considerably. A study from the CEERS team published in late 2024 concluded that the standard model of cosmology is probably not broken. But the same study pointed to a clear gap. Star formation in the early universe was more efficient than simulations had predicted. The galaxies that remain in the dataset, the ones that survived every correction, still formed their stars faster than the models allow, without invoking near-total conversion of available baryonic matter into stellar mass. The physics is not wrong. The astrophysics, the messy layer where gas collapses and ignites, needs updating. That is the pattern. The instrument did not break cosmology. It broke the assumptions that sat between cosmology and observation. The models that translated fundamental equations into predictions about what we should see. The fundamental equations held. The translation layer did not. The second framework that JWST has pressured involves exoplanet atmospheres, and the case study is a world called K2-18b. It orbits a cool red dwarf star 124 light-years away. It is roughly 8.5 times the mass of Earth and about 2.5 times the radius. It sits in the habitable zone, which means surface temperatures could permit liquid water. Before JWST, Hubble had detected hints of water vapor in its atmosphere. After JWST looked at it with 2 different instruments across multiple transits, the picture became more interesting and more contested. The telescope confirmed methane and carbon dioxide in the atmosphere and found very low ammonia. That combination is consistent with a theoretical category of planet called a Hycean world, a hydrogen-rich atmosphere over a global liquid water ocean. If such a world exists, it would be unlike anything in our solar system and potentially habitable. In 2023, the team reported a tentative detection of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by marine phytoplankton. The detection was weak, barely 2 sigma, meaning a 5% chance of being noise. The initial observation used JWST's near-infrared instruments. In April 2025, a second observation using the mid-infrared instrument, a completely independent measurement at different wavelengths, confirmed the signal at 3 sigma, a 0.3% chance of random occurrence. The team's lead investigator described the planet as potentially teeming with life. The scientific community's response was more cautious. Other groups, reanalyzing the same data, found weaker or absent signals for some of the claimed detections. Laboratory experiments demonstrated that dimethyl sulfide can form through photochemical processes without biology. The molecule was detected in cometary material by the Rosetta mission. And a NASA-led reanalysis published in mid-2025 found no conclusive evidence for dimethyl sulfide at all, while confirming the water-rich nature of the atmosphere. The biosignature that made headlines may or may not exist in the data, and even if it does, it may or may not require biology to explain it. If that sounds unsatisfying, consider what it replaced. Before JWST, there was nothing to argue about. What JWST accomplished with K2-18b goes beyond the question of life. The instruments can now attempt to measure atmospheric composition of a habitable zone sub-Neptune at a distance of 124 light-years, and the resulting data is rich enough to generate genuine scientific disagreement about what it contains. That disagreement is the product, not the failure. Before JWST, the question of whether K2-18b's atmosphere contains biosignatures was unanswerable. Now it is answerable but contested, which is where science actually operates. The third area where JWST data has reshaped models is less dramatic in headlines, but arguably more foundational. It involves how planets form. Theories had long proposed that icy pebbles forming in the cold outer regions of protoplanetary disks should drift inward toward the star, delivering water and building material to the rocky planet zone where Earth-like worlds assemble. The mechanism was predicted but never directly observed because it operates on scales and at wavelengths that previous instruments could not resolve. JWST's mid-infrared spectrograph changed that by studying water vapor distribution in 4 protoplanetary disks around young sun-like stars, all estimated to be between 2 and 3 million years old. The telescope found a clear pattern. Compact disks, the ones without gaps or rings to trap material, show enhanced water vapor in the inner disk, consistent with icy pebbles drifting inward from beyond the snowline and sublimating as they approach the star. Extended disks with ring structures show less inner water vapor because the rings act as physical barriers that hold the pebbles in place and prevent delivery to the center. The distinction is clean, repeatable across the sample, and matches the theoretical prediction almost exactly. This is a confirmation, not a surprise, but it matters because it moves pebble drift from theoretical necessity to observed phenomenon. The building blocks of rocky planets, including whatever process assembled the one you are standing on, are being delivered by a mechanism that the models predicted and the telescope verified. In a field where most of the JWST headlines have been about things going wrong with predictions, this is a case where a prediction went right, and the confirmation sharpens the question that follows. If pebble drift works, why does the architecture of planetary systems vary so widely? 3 frameworks. Galaxy formation. The models underestimated early star formation efficiency and missed an entire category of objects. Exoplanet atmospheres. The instruments can now generate data rich enough to argue about, which is a threshold crossed. Star formation. A long-predicted mechanism confirmed, tightening the constraints on what comes next. The phrase model breaking gets used loosely, and it is worth being precise about what it means. A model breaks when the data falls outside the range of outcomes the model permits. That is different from a model being wrong, and the difference matters more than you might expect. Newtonian mechanics is wrong at relativistic speeds, but it works for everything at human scale. The galaxy formation models that JWST challenged were not wrong about how gravity assembles matter. They were wrong about how fast gas turns into stars inside the first gravitationally bound structures, and they were wrong about the role that early supermassive black holes play in shaping their host galaxies. The correction applies to the rates, the efficiencies, the dust production timelines, the feedback loops between black holes and their host galaxies. The plumbing, not the pipes. JWST was designed to see the earliest light. It is doing that. But the value of seeing the earliest light turned out to be less about confirming what the models predicted and more about revealing where the models were quietly relying on assumptions that had never been tested at those distances and those timescales. The telescope did not break the universe. It broke the comfortable distance between the equations and the sky. And if you are paying attention, that is the more interesting result. That distance between what models promise and what instruments confirm shows up everywhere in science, including when the promise comes not from a gravitational equation, but from an engineering timeline, and the instrument measuring the gap is not a telescope pointed at the sky, but a flight recorder pointed at the ground.